So in this video, I'm going to show you how to derive and then apply Euler's midpoint method for solving first-order differential equations. If you want to work along with me in this video, you can download a copy of a PDF from my website. I'll leave a link in the description below. With this equation, we're trying to find the value of y1, which is this point here. We're going to find it by considering the gradient of a curve halfway between x negative 1 and x1, so at a point x0. And we can see that the gradient of a tangent at this point is approximately the same as the gradient of a line segment between the x negative 1 and x positive 1. So we can say that dy by dx at x0 is approximately the difference between y1 and y negative 1, so between here and here, divided by change in y divided by the change in x, so x1 and x negative 1. But you can see from our diagram that our denominator here is simply 2h. So we can say that dy by dx is approximately y1 minus y negative 1 over 2h. Then to work out y1, well, we can move the 2h over to the left-hand side. So we get 2h times the gradient at xo be approximately y1 minus y subscript negative 1. And then we can move this to the left-hand side. So we get y1 will be approximately y subscript negative 1 plus 2h multiplied by the gradient of the curve at x0. Okay? So this allows us to approximate the value of y1. But say if you wanted to work out y2, our point up here, then we can convert this into an iteration formula. If we look at x0, this one here, being the current iteration, well then the next iteration will be r plus 1, will be approximately the previous iteration, r negative 1 plus 2h times the gradient at the current iteration, r. And this is the formula for Euler's midpoint method. In the next example, I'm going to show you how we can use this. Okay, so here we've got an exam style question. We're told that a curve passes through the point 3, 2 and satisfies this differential equation. We've been asked to use the midpoint method with h being 0.1 to estimate the value of y at x equals 3.2, and then to give our answers to 3 decimal places. Okay, so the first thing we need to do is we need to create our table. We have our iteration r, the value of x at that iteration, the value of y, and the gradient, dy by dx, at that iteration. We know originally, when r is 0, we've got x equals 3 and y equals 2. So we can say that at 3, 2, we can work out our gradient, so dy by dx will be the square root. We'll substitute the 3 and the 2 into our gradient equation. So we've got 3 squared, 9, plus the 2 plus the 1. So this will be root 12. And I'll substitute that into our table here, root 12. I'm just going to section off of a table. So then for our first iteration, when r is 1, we're told that h is 0.1, so we're moving across by 0.1 in the x direction for every iteration. So x will be 3.1. And then we can work out y1. But if you want to work out y1, then we can see that r must be 0, and we can't work out y of negative 1. So we can't use a midpoint formula for y1. What we have to do is use Euler's original equation, where y1 would be y0 plus h lots of the gradient at x0. Well, we've got y0, we know this is 2. We know h is 0.1, and we know the gradient we've just worked out as root 12. This will give us y1. We can work this out and we get 2.3464. So I'll put this into our table. And now we've got x1 and y1, we can work out the gradient at this point. So at 3.1 and 2.3464, we know dy by dx will be the square root of the x squared, so 3.1 squared, plus y plus the 1. And we can work this out into 2 decimal places, we get 3.60. So I'll put this into our table. And now we can work out the second iteration when r is 2. We know x2 will be 3.2. And to work out y2, now we can use the midpoint formula. Right, just delete all of this. So we want to work out y2. So we can see that r must equal 1. So this will be approximately, the 1 take away 1 will give us y0 plus 2h, and then we've got dy by dx for r, which is 1. So we can substitute in our values. We get y0, which is 2, plus 2 lots of 0.1, so 0.2. And then we want the gradient at our first iteration, so 3.6. And we can work this out, and to 3 decimal places, we get 2.720. Okay? So this is our final solution. So I hope that's given you an idea on how we can use Euler's midpoint method to solve first-order differential equations numerically. If you found that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link in the description below.